Okay, so I have a new camera here that is going to, I think, work a lot better. I'm going to show you some video that I shot with it yesterday, and then you can be the judge. So I can get to about there. Oh shit. So that's a pretty good window there that we can see. I hope that you watched what I asked you to watch, the introduction kind of review of some stuff. And I hope my audio is better because I'm wearing a mic now, which is a little bit nicer. So let's see, can someone turn the projector on? Over there in that corner there's a button, top left says on. Anybody that wasn't here last time? Anybody need a name thing? Make sure you have your name thing out. If you don't have it out, I'm going to call on you for sure. Let me pass back your quizzes from last time, which were your how you doing things. Everyone got 100 if you were here. Please take yours out and pass them around. I did read these, interesting comments, especially the things, what is a good instructor, what is a good student. And maybe if you could kill the lights that are one switch furthest to the left. This one's wired backwards. Never mind. Do it the other way around. Sorry. It's still messed up. Yeah, that'll work. I'll get better and faster at getting set up. All right. This is to be expected first time through here with this equipment. Where's my mouse? What the heck? All right, so a couple of things I wanted to point out. Everyone? On YouTube, something I wanted to point out. The videos are going to look more like this. This was my Cal 2 class yesterday. The audio, don't worry about the audio, but let me blow this up and go bigger. So I wanted to just make sure you were aware of the settings over here that you can select the quality. And this will depend on your streaming speed. So if you are set at home to do 240p, then this resolution's probably not going to be that great. It's so low it doesn't even know what to do, it looks like. So just be aware that you can switch. You can switch the resolution on that. If it looks grainy, try a higher res. And on the videos that you're supposed to watch for class, the ones I had you watch, let's see where are my playlists. They're in here. They're under what are called the course videos. Where are they? Class videos. Where the heck are they? I don't see them. I was just looking at them. Oh, here we go. So on these, I asked you to watch 1.1 and 1.2. I know that the audio sucks on these. I did these years ago. My microphone was terrible. But But there's also that selection here for quality. And if you do like 480p on this, it's really hard to make out like my graphs and numbers. But if you up that to I think 1080p, it'll do all the way up to 1080p. You can see all the little details, and it's much easier to watch. So I just wanted you to know that, FYI. All right, let's get today's notes up here. So what we wanted to cover was 1.1 and 1.2, and hopefully you watched the video. Yeah? How many of you honestly watched the videos? Okay, good. Then you know that I'm just going to do a couple of examples from the end of that, right? And were there any questions on anything that I covered in here? No issues? I was going to give you a quiz today, but I didn't. It was going to be this. I'm wondering how you would have done on it. I was going to give you a graph, something like this, and I was going to tell you where like certain points were, like here, like give you the values. I was going to ask you where the function was positive, where it was negative, where it was 0, where it was increasing, where it was decreasing, where it was constant. That's what I was going to ask you to do as a quiz today. But I decided I'm not going to give a quiz during the first week, and so you don't get a quiz today. But be prepared from now on. If there's an expectation that you were supposed to do something, that you have done it, and that if you've had a question on it, you've asked me or got help tutoring or whatever it is. We need more seats. Got something? We need more tables, man. I don't know what to say. You gonna be able to work something out? Okay. Maybe you guys can rotate a little bit of the table, like so he's not, no, other way. You know what I'm saying? Yeah, and that way you can kind of look to the side a little bit, and he can not be just back to me. All right, can we get the lights back on, please? Thank you. All right, so we are going to start with the examples here. Determine the implied domains of the following functions. So we want to make sure we understand that when someone gives us a function, we need to be able to recover from it the domain. What does implied domain mean? Implied. So I'm doing 1.1.18, and given a function f of x equals x squared minus 4 over x squared plus 7x minus 8. So we'll start at this table. And I'm just going to go with, I'll go with Ryan. All right? Call out Ryan today to start us out. So can you explain to us what implied domain means? Like, I think we all understand what domain is, but by them saying implied, is that anything different?
That's assuming that, I guess you assume any point can be graphed on the graph.
Okay.
So, I guess it would be negative infinity to positive infinity, or because you don't want to, you can't end up with a 0 on the bottom.
Okay, so you can't end up with the 0 on the bottom. I agree.
And in that fraction, it doesn't look like you, well, you may be able to.
So you think you could get 0 on the bottom? Y'all think you could? Yes? When we write down the function here, did I say anything here like accept these numbers? Did I tell you to hold anything out? No, but it is implied that you must hold some things out. And so what we mean by, determine the implied domain means, even though they didn't explicitly tell us what to remove, let's go ahead and say what they meant for us to. It's implied that it's not there, that certain values of x are not allowed. So all we're concerned with here is the denominator. Because when you have a rational function, and that's the only thing that we have algebraically here that could cause a problem, division by 0 is not allowed. So we're going to address that. We want to make sure that that bottom can never be 0. So all we have to do is ask ourselves, when is it 0, right? When is that 0? Wherever that happens, we throw those answers out. So we factor this out. What is that factor to be here? Plus 8 minus 1. Set each factor to 0. We have two solutions, right? Negative 8 and positive 1. Those are the two x values that make our denominator 0. We do not want those, so we chunk them. So what is the implied domain? I'll give you two ways of writing it. First of all, set notation. The set of all x's such that x cannot be equal to negative 8 and x cannot be equal to 1. That's the domain. This is what we call set notation. The braces mean you're defining a set of numbers. You're defining the x values such that the x's can't be this. Now you could go one extra step, although in this class we don't necessarily need to, because it's also implied. Let me put it out here at the front. You wouldn't need this, but if you're going to go on and do more math, you would want to be a little more explicit, and you would say something like that, which would mean you're saying the set of values of real numbers. So these are numbers we're talking about, real numbers, such that you're not, the set does not include negative 8 and does not include 1. See, later on you realize that there's actually more than just the real numbers. There's the complex numbers, and your set of numbers can be more than just what we're used to having. So we have a way of actually saying the pool that we're picking these out of. That make sense? Okay, so now that's it. Interval notation. How do we write this? Well, remove those points from our number line with interval notation. So you all have seen this before? Yeah, parenthesis, negative infinity, to negative 8, parenthesis, union, negative 8, to 1, union, 1 to infinity. Good. So that would be the interval way of saying it. And you should be comfortable with both notations. I've seen, again, some people will put x, e. Oh, what does that little e mean? It's not the e from college algebra. This actually just means element of. Not to be confused with e, which is the natural base of the exponential function, 2.718, something like that. So not to be confused with that. That means element of. So we're saying x is an element of this interval, or these intervals. Here, x is an element of the real numbers such that x can't be those numbers. All right, next example. Any questions? All right. G of x is x over square root 4x minus x squared. So we want to be able to talk about the implied domain here. We again have an issue that we could get division by 0 here, right? That could be a problem. But we have an additional layer of problems added on top of it, which is that we have a square root, and we know that we don't want to have a square root of a negative number, right? Why don't we want a square root of a negative number? You're going to get an imaginary number. Okay, so why not just keep going? We have imaginary numbers. Why not keep, why not work with them?
It can't be greater than 0.
What?
The conservatism, like greater than or equal to 0 or something.
If you take a number, a positive number, and you plug it in here, your answer will always be a positive number or 0. But we can't have a negative number under the root. If we have a negative under it, like let's say it came out to be negative 4, we can't do that. Well, we can, but we can't. We know it involves imaginary numbers, but everything that we do in this class, everything that we do in this class, in this book, Cal 1, 2, and 3, you are not allowed to work with the imaginary numbers. Okay? This book doesn't say it in it, but a class like this is called Calculus of a Single Variable or Single Real Variable. And then you get, later on, Cal 3, it's called multivariable calculus. But again, you're still dealing with real numbers. You don't get to imaginary numbers. You don't get to play with those and do calculus with those until after you've taken Cal 1, 2, 3, linear algebra, differential equations usually. Once you get those out of the way, then you're ready to bring the eye into the game. And it changes. I mean, there's a reason why they do it. It's geometric. It's four-dimensional space. It's not as easy to visualize. So you have to wait till you kind of mature a little bit mentally, like mathematically mature, and then you can handle it. So that's the idea. So for us, this domain, we're going to throw out the possibility of having a negative under there because you don't want to deal with eyes. So it's a twofold problem. First of all, I'm asking myself when this happens because I don't want this to happen, right? Because if this happens, this is 0, square root of 0 is 0, division by 0. So where does that happen? Just factor it. Right? The two solutions are 0 and 4. So setting each of those to 0, you get 0 and 4. So I know that I don't want those there, right? I do not want those there. So maybe I'll make a list over here on the side just to keep track of things. I do not want x to be 0. I do not want x to be 4. All right. But additionally, okay, separate idea is that the thing underneath the square root, what do we call the thing underneath the square root? Radicand, yes. The radicand must be greater than 0. Now, why didn't I put greater than or equal? Because can't you take the square root of 0? Yes, but if it's 0, then I'm this, right? And I've already looked at that, and I don't want that. So I'm just saying, look, I need this to happen, right? I need this. Right? I need this to happen. Just to clarify, this one, no, don't want this, right? I just don't want you to think that what I'm putting up here is, this is what I need and I needed that. These are kind of opposite trains of thought. So what type of thing is this? What do we call this thing right here? Our answer is going to be interval, yes? Is this an equation?
No, it's an inequality.
It's an inequality. And it's more than just an inequality, it is a quadratic inequality. Melina, do you remember we had this in the class and you asked me on the board whether or not you could do it that one way and I told you? Remember that?
Yeah.
It's exactly this. Yep. So what we're going to do in order to figure out what this is, okay, the way you solve a quadratic inequality is first you turn it into an equation. That's the first thing you do. So if you need to go back and look this up, go look it up. Quadratic inequalities, how to solve them. I set it to an equation first. What are going to be the, I set it equal to 0 first. What are the solutions when I set it equal to 0? We already did it, right? 0 and 4. Right? X equals those. And then what we do is we plot those on a number line. See if this starts to ring a bell at any point. This partitions our number line into 3 sections. And what we do now is we pick points and we test them. And we see if the inequality comes out to be true or false. Does that ring a bell at all? It may have been a while, back in college algebra. So I'm going to pick some points and I'm going to check them. And I'm basically going to give it a thumbs up or a thumbs down. And I'm checking it up in here. So to the left of 0, -1. Plug -1 in here. Does it work? Yes? No? No, it will not work. Yep. It'll come out and it'll be a number that is actually smaller than 0. Now I plug in a number between 0 and 4, like anything I want. 2. Plug 2 in there, it does work. Plug in something bigger than 4, put it in, it doesn't work. So it turns out that the only things that do work are the numbers between 0 and 4. Right? Now another approach to this, which I prefer, is that if you kind of just take everything, all this out of here for a second, and just look at this, you're saying that's a parabola, right? And you want to know when that parabola is bigger than 0. That means you want to know when that parabola is above the x-axis. Yes? And this parabola opens up or down. down because of the negative in front of the x squared. So I know this parabola looks like this. And I also know from what I did over there that it hits at 0 and 4, which means that it must look like this if I were to graph it. Right? Which means that between 0 and 4 has to be above the x-axis, has to be positive. So you can do it without any checking of test points if you just understand what that looks like. I prefer that way, but you know, we have to have a method. If this were, you know, 4th degree and 7th degree, then you wouldn't know what that looks like necessarily, so you would have to do testing regions. All right, so let's put this all together. I want the numbers between 0 and 4, but I don't want 0 and 4. So how do I say that in set notation? In set notation, the set of x, and again, I'm not going to put in real because we know we're dealing with real numbers. And then you just put your bounds on x, 0 and 4. The set of all x's such that x is between 0 and 4. In interval notation, what would it be? Do we want
No, it's 0.
0 to 4? That's it. And again, you could put x in element of that if you want. Questions? Okay, next one, secant x. H of x is secant x. It's our last one. Well, you took Precal, right? So I expect that you all remember the secant function. The secant function is the reciprocal of the cosine function. And we saw in last class to draw a secant, you really can just draw a cosine and then create your vertical asymptotes and then draw your little u's on top and bottom and you'd be done. What this is basically asking is where do those vertical asymptotes occur, right? Where is this thing undefined? So it might be easier to look at it this way because I think cosine's a little bit easier to deal with. What we want to know is what's going to screw that denominator up, right? What's going to make it 0? So where is cosine 0? What's that? Pi over 2? 3 pi over 2? Okay, so now this is where we're really going to tap into how good your pre-cal was, all right? Pi over 2 and 3 pi over 2, those are correct answers. But it's not the correct answer. Because I didn't tell you you can only look between 0 and 2 pi. I need all the answers. And there's infinitely many of them. So how do we write it? So we have to make sure we understand how do you write all these answers. So some people in pre-cal, they learn to figure out where cosine is 0 by looking at the actual cosine curve, like this. That's how some people do it, and they just know this happens here, and they know all that. Some others, and this is the way I teach in pre-cal, is I always go off the unit circle. The unit circle to me is like the magic pill, okay? How many of you, raise your hands, feel more comfortable on the unit circle? Okay, anyone feel more comfortable on the graph? It's okay. No? Okay, good. We're all unit circle people then. So here's what I'm going to do. Just, again, this is a review day kind of. We're still going over concepts you should know. If I'm saying where is cosine of x is equal to 0, it says tell me the angles that give you 0 as an x coordinate, because cosine always is associated with the x coordinate on the unit circle. Sine is the y coordinate. So where's my x coordinate 0? Up here, right? And right there. Now we could look at that as 90 degrees and 270, or we could say pi over 2 and 3 pi over 2. You should be comfortable both ways, and you should start to prefer radians. Degrees kind of at some point goes away. I mean, not goes away, but it just becomes the less preferred way of dealing with things. So if that's pi over 2, straight up is pi over 2, and the one down here is 3 pi over 2, I need to remember that I could be a pi over 2, and I could actually rotate all the way back around, and that would still be a correct answer, and I could go all the way back around again, and that would be the correct answer. So I can always add 2 pi multiples, or subtract 2 pi multiples, right, to get back to this point. But I can be even better than that, because the points this point is actually straight across from this point. I can actually jump from one to the other by adding, instead of 2 pi, just pi. So if I go from here and I go add a pi, I'm here, add another pi, I'm back up there, add another pi, I'm back here, right? So I can start with this solution and start picking up the one on the bottom, just going like this. Well, I should go slower. Here, 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 like that. So how do I say that? My x, my angle, must be starting at pi over 2 and then adding to it half rotations, which is pi, and any multiple of that, n pi, or you could write pi over 2 plus k pi. Different books do it different ways. N or k, you should know that books use both n and k to represent these counting numbers. So what I'll stress also here is that n and k are both elements of, it's a double struct, it's a script z, which is the integers. I did this earlier, right? And it said real numbers. I hate to do this, but my phone just will not stop going. Okay. All right. This means integers. This is all real numbers. Integers are what? 1, 2, 3, 4, 5, 6, 7, 8, 9. And negative 1, 2, 3, 4, 5, 6. And 0. So this n and this k can be any counting number, positive or negative, but it can't be fractions. So you can't let n be a half. That screws it all up. All right, there we go. Questions? That's our answer. Oh, x cannot be that, right? X cannot be that, because that's what causes the problem. So let me write it in set notation. The set of x such that x cannot be pi over 2 plus, you want to do n? N pi, okay.
I got lost.
Yes?
Okay, so I know where you got the pi over 2,
Mhm.
but I got lost where you got the n and the k.
Okay, well, these are just two different answers. Pi, if I take an angle and I add pi to it, that's a half rotation. And those 2 points were directly across from each other. So to get from this point to this point, I add a half rotation, which is I add a pi. Then to get back up here, I add another pi. Then to get back down there, I add another pi. So if I start at pi over 2, that's straight up, and I add any multiple of pi, I'm going to be at one of those two answers. And if I add every multiple of pi, I'll get all infinitely many. That better?
Yes.
Okay. How about interval notation? That one's a little harder. How would you write interval notation? Don't you have an infinite number of intervals? We could still do it, though. Let's see. Let me draw the picture. I'm drawing the picture of... I'm drawing secant real quick for us. Okay, that's what secant looks like. It's a cosine curve, and then everywhere the cosine is 0, it's undefined, so I have my vertical asymptotes. Where is this first one occurring? Right here. That was pi over 2, wasn't it? So my graph is defined between pi over 2 and what? What's this next one over here? 3 pi over 2. Yeah? So would you agree that this length of this interval, if I just move it over, that interval is also good? And the next one is also good. And the next one is also good. How much does it take to move this over? Like to move this point to this point? How much, what's the length? It's just pi, right? Just pi? So watch what I could do. I could say x is an element of open parentheses. Okay, so this is not a bracket. It's not including the endpoint. How about starting at pi over 2 and ending at 3 pi over 2. Do you agree that that interval is in there? I left spaces for a reason. Do you agree that x can live in here? That would be between these two, right? But I could shift both of them over by pi, and that next interval would work also. So I could say plus n pi plus n pi. Same n for both. So if I say n is 1, it's going to move both of these points to the right by pi, isn't it? And that will actually get this point to jump over like this. And then you let n be 2, and now instead you jump twice. You go here and here again. And so that will peel off every single interval. And it removes all the little points that you don't want. In my mind, that's much easier to write. But we should know that there still is a way of doing it this way. Any questions? We're okay? All right, now we're moving on to the next example. 1.19, which has us trying to determine whether or not we can express some things. Express the area of a circle as a function of its diameter. So what we're practicing right now is, if you know something about a geometric shape, can you relate the quantities together? And can you relate it in the way that you're told to relate it? So we're trying in this problem to express the area as a function of its diameter. So before I even begin, can somebody tell me about the area of a circle and something you do know about the area of a circle? Bless you. Anyone know, if you have a circle, what its area is?
A equals pi r squared.
A is pi r squared. That should be a known formula. If you don't know it, maybe you now remember that you've seen that before. That's on your formula sheets. Does anyone have them today by chance? Did anyone print them out? Yeah? Are they handy to you right now? Okay, you don't need to take them out. It's on the first page. On the first page of the formula sheets, there are a bunch of formulas for different geometric shapes. All right, so just be aware, you're allowed to have that. You're allowed to bring that to class. I would hate to give you a quiz next time and ask you to do some relationship on some formula and you don't have those. Because I'd be like, well, you're allowed to have them. So you either have them memorized or you have your sheet. So one or the other. This one. This equation right here actually determines the area as a function of radius. You could write it this way. Area A of r is pi r squared. Now we don't normally write it that way, but I'm just trying to get you to understand that if somebody gives you the radius, you can determine the area exactly, can't you? So we'd say that the area is a function of radius. Is the radius a function of the area in the way it's written? No. R is not solved for. So it's not the other way around. But we'll get to that. What is this one asking us? Express the area as a function of diameter. So what I want is this, or what we want to be able to do, is express the area as a function of capital D, where capital D is the diameter of the circle. So how can we do this? Let's go with Chris's table back there. I'll let anyone from Chris's table.
Could you write it as pi 1/2 capital D squared?
I'm just going to write that right here. Pi, and then you said 1/2 capital D squared. Want me to do anything else? It's almost right. I'll let you look at it for a second. No one say anything. While they're thinking about it back there, I believe what's happening. What's your name? Edward. Where's your thing, Edward?
I forgot it at home.
Here, I brought extras. You can make another one. Who needs them? Okay. If you forgot it, then I won't bring extras every day. Y'all need to remember to bring these. There. So Edward, I believe what Edward's doing is he's just writing down a relationship he knows between the radius and diameter. He knows that if you take, that the diameter of a circle is always twice the radius, right? That's all. Or if you solve this for r, you could say that half of the diameter is equal to the radius. And then just taking this formula, which we already knew, and replacing the radius with half of the diameter. Yeah? Any updates on this? Anything you want me to do differently?
Thanks, right. The 2r d.
You're going to replace the r with 1/2 d. Because we solve for r here, and we're replacing that r right there with half of d. Okay, now open up to the classroom. Add a parentheses. Right there. And that's because you have to square this quantity, right? And if you don't put the parentheses, you really are only saying to square the d. But you have to square the 1/2 also. So now let's actually square it. What happens if you square a half? Half times a half, a fourth, and then d squared, d squared. Now you can go without the parentheses. And so you get something like this, pi over 4 d squared. The area as a function of the diameter is pi over 4 times d squared. So what's the advantage of having this formula over this formula? Well, let's say it's easier for you to measure the diameter of a circle than it is the radius. Then you don't have to keep converting over and over and over. You have a function that will take care of it. You just give me the diameter, I can spit you out the area. Any questions here? This was as straightforward as they get because the conversion over was pretty simple. The connection between radius and diameter was about as basic as you can ever get, right? How about the next one? Express the volume of a cube as a function of its surface area. So I'm going to let you all play with this one for a little while. All right, see if you can get that one. That means you can talk to each other. And what I'd like, we're going to make this a race. Okay, so the first table that gets it, all right, will get some sort of reward for it. First table to get it, write the answer on one of the boards. This means y'all have to talk to each other. It kind of sucks. If y'all need to like get your phone out and Google something, there's a problem. I don't want to say. No, you should, if you need a book, you know, you have to know what a cube is, right? See if y'all can deduce it. I don't want anyone looking anything up that would be an advantage. Draw pictures.
Did you say no looking at?
Oh, like on your phone. If you have your textbook and formulas, that's okay. Just no getting on Google and looking up anything.
Whatever the length of the side is. And itself 3 times. So yes, and we don't know the length of that, so we call it X, so we can call it Y. The surface area here. I'm gonna say no can do. No. But I have. Area of a square. So if it's 1 square.
No, I mean, there you go.
Okay, so let's see.
Anybody feel like they're getting close? Yeah. Anyone feel close yet? A little bit?
What's the surface area?
Because that's the volume.
Yeah, that's the other one with the D2.
So would it just be
Is what?
The volume, but it's a function of its surface area.
That-
So we're trying to figure out that formula.
For the surface area?
X cubed, doesn't matter.
That's right.
Yeah.
The volume is x cubed, if x is the length of the side.
Right.
Uh-huh.
Any side,
So that would be the volume in terms of the length of a side.
yes.
You want the volume in terms of the area. So what do you know about the area?
It's length times width.
Okay,
no way just time?
kind of. Draw a picture. Draw a cube,
Yeah, okay.
all right?
There's my cube.
Okay.
A little bit real big.
So tell me about the volume. If you're saying the volume is x cubed, where's x on your picture?
X is any side.
Okay. Go ahead and draw it.
X?
Yeah,
Okay,
sure.
X is right there.
Okay. Now tell me about the area again.
X is length times
How long's your length?
whatever I define X as.
What's the height?
X
X.
Okay.
times X.
Okay? So that's the area of what?
Of one,
Okay, how many are there?
there's six.
Okay, so you're starting to get to it.
Yeah.
You're introducing length and height you don't need to. Right? The length and height is always the same because it's a cube.
Right.
All right, I think there's more, I don't know if confusion is the word, but there's more lost than found right now. So let me help you with this, all right? A little bit harder than the first one, right? All right, so you have a cube. We all have to understand what a cube is. Okay, so if you're trying to draw in 3D, you draw the front face of the cube, which is a square, and then just take each corner back like this and drop down and over, something like that. There's a cube. And because it's a cube, by definition, all the sides have to have the same length. And so I can call it L, I can call it H, I can call it K, I can call it whatever I want, but I'm going to call it X. Okay, so here's X. That means this is X, that means this is X. All of these are X's, right? X everywhere. What is the volume of this thing in terms of X? X cubed. Because the volume of a box is length times width times height. Right? So that, I think a lot of you got that part. But now you have to discuss the area of this. And I'm going to write down next to this, volume is X cubed. I'm going to take the V of X out and just put volume as X cubed. Now the area, I have to look at the area of, let's just look at the area of this front face. What's the area of just that front face?
X squared.
X times X, because it's the same width and height, right? So X squared. And how many sides are there on this? 6. So would you agree that the area as a function of X is 6X squareds? Which means that the area is 6X squared. All right? And what we want, okay, what we want is the volume in terms of the area, right? We want the volume as a function of its area. So I need to somehow connect these two together. Right? That's what I need to do.
So just put A in for the value of X.
Close. What did we do on the previous problem? We had R in there, and we needed to have D in there, right? We had D is 2R. In our equation, we had the R, and we needed to replace it with D. So what we did is we took this equation, we solved it for what? It's already solved for D. We solved it for R, didn't we? And we got half of D was R, and then we took that expression and replaced the R with this. Same exact thing. I want this in terms of area. Right now, my area has X in it, and the volume that I want has X in it. So why don't we take this equation and solve it for X? If we solve this equation for X, I can replace that X into this formula, and it'll be in terms of A. That's what I'm going to do. So I'm going to try and write down this equation solved for X. So how do you solve for X there? What would be the first thing you'd do? How about divide both sides by 6? Now what?
Square root.
Square root. Square root on both sides. Now we know that anytime we take a square root, we're supposed to do plus or minus, aren't we? But because X represents the length of a side of a cube, I can throw out the idea of it being negative. So it's okay, just use the positive one. And that's what X is. So now come back to your volume formula. You know that the volume is whatever X is cubed. So that's what X is. So won't this be the square root of 1/6 A cubed? Isn't that what that means? That's it. You could clean it up a little bit, but I mean, that is the volume in terms of area. So if someone gives you the area of a cube, you can, with relative ease, you could compute the volume. So what if the area of a cube was 6 square feet? What's the volume? So if I tell you that the area of a cube is 6 square feet, what's its volume? 1 cubic foot. So you just plug 6 in here. 1/6 of 6 is 1. Square root of 1 is 1. 1 cubed is 1. So I made it where it would work out nice. But it would be 1 cubic foot because now you're talking about volume instead of area. All right. Express the surface area of a sphere as a function of its volume. That'll be a take-home quiz. How about we do that? Okay? You do that at home. Turn it in first thing next class. Anytime I give you a take-home quiz, I won't say, okay, let me collect the quiz. I just expect it to be on my desk at the beginning of class. Now, when I give take-home quizzes, unless I specify, you can get help on it. You can help. You can work with each other. It's okay. Unless I tell you explicitly, this is you work by yourself, get no help. Assume that anything I say is take home is truly kind of open for you. All right? And don't just go to Google and be like, surface area of sphere is a function of volume, because you could probably find something nowadays. You probably could. But I'll know if you do. I want to see the work, right? I want to see you setting things up, making the connections, solving for the variable, replacing. All right, that takes care of Chapter 1, Section 1. And is there a homework assignment for that? There, on our calendar, there's a homework assignment. Okay, so you all know this schedule we have, right, for the class? There is there's not one for 1.1 and 1.2. Okay, I take that back. So the homework assignments out of the book do not pick up until you get to 1.3. A good student might get to the point where they're like, you know what, I'm going to look at the problems in the back of 1.1 and see if I can, just mess with them. These are review topics. Even though I wasn't told to do that, I'm going to do it just because I want to make sure I'm really on point with what's happening here. All right, 1.2. So what was 1.2 about? You've got all these functions that you're supposed to know about, cubic functions, square root functions, and sine functions, and then how you move them up and down and reflect them and do all these different things to them. We had some things with combining functions together. So I'm going to work through those examples. I think the ones that are most interesting are 1.2.5, where you have two functions given to you. G of x is x minus x squared. And they ask you in here, find f plus g, f minus g, f times g, f divided by g. But the last one is the one that I really want to focus on. Find f, how do I say that? Of g of x, right? This is composition. This is the composition of two functions. It's what you get when you take a function and plug it into another function. So I'm going to take, in this case, because of the way it's written, the order, I'm taking the f function and I'm putting inside of it the g function. That's what that notation means. And that means that I'm going to take the f function and plug into it whatever g was. So g in this case was x minus x squared. This is just a replacement game that we're playing, right? You're just taking one thing and plugging it into the other. So in the f function, I will take wherever I see x, and I will replace it with x minus x squared. And just be careful with the parentheses. So no more f. I don't need to write f anymore because I'm now going to apply f to that expression. It's that expression, then what? Squared plus 1. So this is just about, do you remember how to put a function inside of a function? That's it. Now you could expand this, right? Like you could multiply that out. But this is also okay. Just make sure algebraically, if you had to multiply that out, you could. And then on 1.2.6, I asked to do the same things, but the functions are a little bit crazier. So there are the two functions. And you're asked in the first part to add them together. And the second part you're asked to subtract. And I think the addition and the subtraction here are a little bit harder than the previous example. So I'll do the subtraction just to make sure we're comfortable with that. If you're asked to find f, take away g, that means you write down f and you subtract from it g. And that's correct. I mean, that is f minus g. But what if you wanted to kind of clean this up a little bit? Maybe instead of having 3 separate terms, put it into one term. Could you?
Yeah.
Yes? You would have to do what? Find a common denominator. Which in this case, our common denominator would be what? X times 2 minus x. So we would have to make sure that every denominator had that in it. And if we look across these terms, this has a 1 down there. So what would I need to introduce on the top and bottom here? The whole thing, right? On this one, the only thing I need to introduce on the top and bottom would be 2 minus x, and then here, just x. So I'm going to do that mentally, and then just make sure you see where it all came from. So I'm going to go here, this whole thing on the top and bottom, which would give me an x squared 2 minus x over the common denominator, plus, now on the second one, we said the only thing we were missing was the 2 minus x. So I'm going to introduce a 2 minus x on top and bottom. And then on the last one, the only thing that was missing was what? X, so I introduce it on top and bottom. How do I put that x on the top? Yeah, just multiply it through. So it'll be x squared minus x over the common again. Now what you don't want to do is start canceling things out, right? Because if you do that, you can get right back to where you were. The whole idea was to get a common denominator so we can squeeze it all together. So when we have a same denominator, we put this with this with this all together. Make sure you're paying attention to the signs you have there. Are there any questions on what I've done, though?
So you just found a common denominator and just plugged it in top and bottom?
Yeah, it's kind of like if I have 1/3 plus 3/7. My common denominator is 21, right? So what I have to do is I have to multiply top and bottom here by 7, top and bottom here by 3, and that'll give me 21 on the